Welcome to the After On podcast. I'm your host, Rob Reed, and this is a series of conversations with thinkers, founders, and scientists. Take a little time and stretch out, because these talks are unhurried and meant to bring you to a top percentile understanding of something important. So, whether you're into startups or ideas, a techie or a lit major, take your time, engage your mind, and you'll be glad you did it. Especially this week, when we'll be talking to Harvard Astronomy Department Chairman Avi Loeb. As his title indicates, Avi is an extremely credentialed astronomer. So when he asserted that an object currently passing through our solar system could well be the artificial product of an alien intelligence, eyebrows went up, including my own. He made this argument in a scientific paper published on the 12th of this month in the Astrophysical Journal, which itself is one of the top research publications in all of astronomy. I got wind of this paper before its official release date and reached out to Avi, and we ended up having the longest and most in-depth interview he's given on this fascinating topic thus far. And also, he noted in an email to me yesterday and invited me to share this characterization, the most intellectually stimulating interview from his personal standpoint. Now, I was delighted to hear this because, like anything connected to aliens, this story has inevitably led to an avalanche of soundbites and clickbait. It's also triggered a fair amount of controversy amongst professional astronomers. The negative reactions have ranged from skepticism to something verging on moral outrage. But adversarial debate is one of the key mechanisms by which science advances. There have been periods stretching for decades when the field of astronomy itself was divided over some of the most basic aspects of the cosmos. Is the universe expanding? Was there or was there not a Big Bang? Are black holes a thing or just a theoretical toy? Great minds lined up on opposite sides of these questions for large proportions of their careers. Luckily, we won't have to spend quite so long on the edge of our seats because the debate Avi has triggered has a sell-by date. As we'll discuss toward the end of the interview, much of the mystery surrounding his arguments should be dispelled in a bit over 3 years when a powerful new telescope comes online. After hearing this interview, you should be equipped to make up your own mind about what you expect the new telescope to reveal, if anything, and to follow this story as it unfolds and to debate it in an informed way, if you wish, for as long as it remains a mystery. Before we start, 2 quick notes, one for my most committed listeners and a second for my newest listeners. First, you old-timers, if you are backing this show on Patreon at a level of $5 per month or more, I urge you to turn this version of the episode off right now and go to the episode in the private Patreon podcast feed. As is often the case, that version of the show is significantly longer, specifically the main body of the interview, excluding the intro and outro, is probably about 20% longer. That's 20% more controversy, 20% more astrophysics, perhaps even 20% more aliens. I also posted the Patreon version several days earlier than the main feed version as a second way to thank my patrons for making this show financially possible. So patrons, either go to the podcast feed on your smartphone or go to patreon.com/RobReed, R-E-I-D, to get what you paid for. As for those of you who are new to the show, welcome. I'll tell you more about Patreon and all that stuff at the end of the show. But for now, suffice it to say that you have stumbled upon a podcast which features in-depth conversations with world-class experts about their domains of knowledge. In each episode, I try to bring you and myself a serious grounding in something complex and important that we should all probably understand a bit better. If you enjoy this episode, please browse the show's archives at after-on.com or in your favorite podcasting app. You'll find an archive of fascinating conversations with some of the top people in robotics, neuroscience, cryptocurrency, drones, augmented reality, synthetic biology, and many other fields. If you're interested in these sorts of things, I hope you'll consider subscribing to the show. Finally, some quick background for everyone before we start. The mysterious space object which is causing all the excitement is called Oumuamua, a name Avi and I will cite frequently. It's a Hawaiian name chosen because the observing system that discovered it is based in Hawaii. Avi and I will refer to that observing system as PAN-STARRS, which is a complicated acronym. Oumuamua got its first burst of attention when it showed up about a year ago because it's the first interstellar object, which is to say the first object from another star system definitively identified within our own solar system. And so with that background, I bring you Avi Loeb. Avi, thank you so much for inviting me to your office on what I'm sure must be one of the crazier weeks of your career. But before we get into that, I'd like to briefly review your background just to set some context for our listeners. Starting with the most basic thing, what is your title here at Harvard?
I'm the Frank B. Bird, the professor of science. I'm the chair of the Astronomy department at Harvard and the director of the Institute for Theory and Computation and the founding director of the Black Hole Initiative at Harvard.
And how long have you been the chairman of the Astronomy department?
8 years.
8 years. How many academic papers have you published in your career?
My first paper was in 1985, and since then I published over 700 papers and wrote 4 books. The first, Stars to Form in the Universe, that was my early interest. When I became faculty at Harvard, not many people were interested in the first stars, and I thought of it as an exciting frontier because it's the scientific version of the story of Genesis, how the first light was produced. And most recently, I got interested in the search for life. And in fact, right now, I'm writing a textbook with my postdoc, Manasvi Lingam, on extraterrestrial life from biological signatures to technological signatures.
When is that coming out?
We hope to finish it by next summer 2019. I don't see this subject as speculative at all. I think life is likely to exist out there. We better understand where to look for it. And by the way, an interesting lesson from astrophysics is that the laws of nature were found in laboratory experiments. And then we found them to hold when looking at the universe and interpreting the data that we collect on the universe. And the same thing may happen in the context of the search for life. There are several groups around the world trying to produce artificial life in the laboratory. And if we are successful, then this will demonstrate to us under which circumstances life may develop. And then we can look out in the universe at environments that provide these circumstances. And again, our imagination will be guided by what we achieve here in laboratories.
Is this going to be something that's really for an expert audience as opposed to a popular audience?
Well, there would be parts of it where a popular audience would be able to follow everything, and there would be parts that have equations.
Well, I'll look forward to reading all the non-mathematical parts of that. But meanwhile, let's talk about this mysterious lump of matter that's passing through our solar system called Oumuamua and the response to what you just published about it.
Yes, and this was unexpected. I just wrote a paper that was one out of the 40 papers I wrote over the past year and was surprised to see the reaction.
Well, it's been quite a reaction. And to talk about this amazing object, why don't we start with what happened a year ago, roughly, October 19th of last year.
The Pan-STARRS survey monitors the sky, and the purpose is primarily to find the asteroids that may, in fact, impact the Earth. And they noticed an object that moves so fast that it's unbound to the sun, therefore must be of interstellar origin from outside the solar system.
It was moving so fast that it was going beyond the escape velocity for the solar system.
Correct.
It was 26 kilometers per second or something like that.
Correct. It's the only thing that we spotted that comes from outside the solar system.
And by the way, this kind of blows my mind. A bit of an astrophysics fanboy, always been fascinated by astronomy and so forth. And when Oumuamua first became a story a year ago, it kind of astonished me that somehow over the centuries that we've been gazing at the sky, we had never found something that was definitively from outside the galaxy. I was amazed that it took until 2017 for that to happen.
Well, the reason is simple. These are small objects, and only when they pass close to the sun or close to us, we can notice them. There might be a lot of traffic out there, and it's just that we can't see them very far because we need the sun to serve as a lamppost that illuminates them, and they need to come close to us for us to see them.
Close enough for us to see, and or close enough to the sun to be illuminated.
Right.
And this one was spotted by a new-ish telescope you mentioned. It's called Pan-STARRS.
Right.
It's been up, I guess, since 2010 or so.
Yeah.
So assuming for the moment that Oumuamua is just a typical rock from another star system, how do we imagine it would have found its way here?
Now, these objects, most of them are expected to be ejected from the periphery of the star. That's where objects are not bound very strongly to the star. For example, the Oort cloud has a lot of asteroids in it.
The Oort cloud being very, very distant, way beyond Pluto, where most of the comets hang out, right? When they're not zipping around the sun.
It's about 100,000 times farther than the Earth-Sun separation. And so that's the outermost edge of the solar system. And it's actually roughly halfway to the nearest star. So you can think of stars having these spheres around them, and they're almost touching each other.
The outer spheres, the Oort clouds, almost touch each other, even though the stars are extremely distant.
Exactly. And the outer part of the Oort cloud is where you expect most of the ejections of asteroids to take place, because they're very weakly bound to the sun. A kick by only a few kilometers per second can get them out, or even less than that.
So just to clarify, if something does come through our solar system from another solar system, the expectation would be that it came out of that solar system's Oort cloud because it's got such a weak binding. And as I just mentioned, it surprised me to learn that it took us until 2017 to identify something from outside the solar system, but you were surprised that we identified our first interstellar object so early.
Because even if you make optimistic assumptions that all stars are just like the solar system, they have an Oort cloud, about a decade ago, we made a prediction for how many asteroids should we find with pan-stars. We predicted that we wouldn't find any, and that in fact we have to wait for the next generation, the Large Synoptic Survey Telescope that will come online within 3 years, that will be much more sensitive.
And to be clear, you made that prediction in a paper you wrote right before the Pan-STARRS telescope went live. And you didn't just calculate that Pan-STARRS was unlikely to spot something interstellar, but you put the odds against it somewhere between 1 in 100 and 1 in 100 million.
Yes.
That Pan-STARRS would ever see anything.
Right.
So you were, I imagine, personally quite shocked on October 19th of last year when this thing showed up.
Right.
Because you had done that calculation 10 years ago.
Right,
so you were
right.
probably viewing this through a different set of eyes because you had this background.
Right. And the reason that interstellar objects are of interest is just like having a dinner party and inviting people to it and then realizing that one of the guests is from another country. And by examining that guest, you can learn about the culture of that country without spending the time and money to visit that country. And so that offers great prospects for learning about other planetary systems without the need to visit them. With chemical rockets, it would take us 100,000 years to reach the nearest star. And so it's a very long journey, and these objects have spent already the time arriving to our door. So why don't we take a look and figure out what's going on now?
This is a very, very interesting dinner guest. Now, the object was first spotted on October 19th. It took about 3 days for them to determine its speed relative to the sun, and to determine from that, this is definitely from outside of the solar system. So let's say it's the 22nd, 23rd. But it got closest to the Earth before that. Oumuamua's closest approach to the Earth was October 14th, and its closest approach to the sun, when I assume it would have been brightest, was September 9th. And so we didn't see it until it was already on its way out of the solar system. Why did we miss it when it was on its way in? Because we would have gotten so much more data if we'd seen it coming in.
Well, the survey has an operational mode where it looks at different parts of the sky at different times, and the analysis of the data takes a while, and the alert of interesting objects takes a while. So it was just missed in the early parts of the orbit, and so it was just out of the radar. And it's sort of like having that dinner guest, but not realizing it until he or she leaves the door, and then you realize, oh, that would have been really interesting person to speak with.
Unbelievable! A Panamanian! I always wanted to meet a Panamanian, and now he's halfway down the driveway!
Exactly.
Now I gotta go to Panama City. I'm never gonna do that.
No, you can't, because you just need to organize the next dinner party. Perhaps there would be another one. A good aspect of astronomy is that you have classes of objects that keep coming back again and again. Now, this is under the assumption that it's one object out of a random population.
Once it was established that this was, in fact, from outside of the solar system, the astronomical community did rally. The woman who was in charge of the apparatus in Hawaii, her name is Karen Meach, right?
Right.
She worked very hard, and I'm sure lots of other people worked very hard to get telescope time on lots and lots of telescopes. Lots of teams started tracking it. The Hubble got involved. How unusual of a surge was that?
It was not sufficiently unusual. I think the next one around will get much more attention. In reality, it's a very peculiar object because it reflected sunlight and it rotated roughly every 8 hours. And its brightness changed by a factor of 10 as the object rotated. And so that told us that it has a very extreme shape. It's at least 5 to 10 times longer than it is wide.
So it's sort of flashing. It's flashing somewhat erratically. And if I'm not mistaken, the aspect ratio of ranging from 5 to 10 to 1, that's really weird. Like the outer limit for natural objects that we're familiar with is 5 to 1, right? And if it was as long as 10 to 1, is that unprecedented?
That's unprecedented. So there is actually no other object, an asteroid or a comet in the solar system that had such an unusual axis ratio.
And another unusual thing was Oumuamua's speed in relation to our immediate neighborhood in the galaxy.
Yes, the speed is an interesting story by itself because this happens to be the so-called local standard of rest you get when you average over all the stars in the vicinity. So stars have relative motion to each other, and so you can take the average of that motion and find the local standard of rest. And it so happens that Oumuamua is originating from that frame of reference. It's almost at rest relative to the local standard of rest. And only 1 in 500 stars is so slow relative to this frame of reference. Now, if you wanted to camouflage your origins and hide where you came from, you would be in that frame because that frame does not belong to any star. Only 1 in 500 stars is in that frame, and Oumuamua is in that frame. And it's sort of like a buoy sitting on the surface of an ocean. That fact by itself is very peculiar because the speed of a star is typically 20 kilometers per second, like the sun is moving relative to that frame of reference.
So let's say Oumuamua was ejected from an ordinary star, not one of the very rare stars that happen to be traveling at precisely the local standard of rest. What would happen next?
For these objects to be ejected, they need a very small kick. And so they would primarily move at the speed of the star itself.
The star that they're orbiting.
Yes. And so then it would be surprising to find Oumuamua as the very first encounter being at rest in this local standard of rest because it would have the characteristic speed of its host parent star from where it came. And so just the velocity tells a whole story that is completely unexpected.
How large of an area does the local standard of rest apply to? Is it the entire galaxy?
No.
Or a 500 light year sphere?
The stars move relative to each other, but they all move around the center of the galaxy together.
They move around the center of the galaxy together. So the region that defines the local standard rest, there's what, 100, 200 stars roughly?
There could be more. Altogether, it could be thousands of stars over which you average.
It's a pack of stars.
Right.
They're moving kind of as a pack, but they're also moving at pretty high speeds relative to one another. And when you look at that pack, the definition of the local standard of rest is averaging out all of those different speeds. And then what's remarkable about Oumuamua is, in one way of looking at it, it's not moving, it's stationary.
Right.
It's at that local standard of rest. And you said within our pack, it's only 1 star out of 500.
Right.
There's really just a 0.2% chance that by sheer happenstance, it would be at the local standard of rest.
Yes, and moreover, you need the directions to coincide. So in other words, it could be that there is 1 star out of 500, but at a completely different direction. So there are 2 coincidences you need to arrange, one in velocity space and the other one in position space.
So by being at this local standard of rest, Oumuamua, by one definition in relation to our pack, is stationary. And when it comes through our solar system, it looks to us like it's coming through at 26 kilometers per second. But another way of looking at it, and perhaps more accurate, is our solar system is sweeping past it at 26 kilometers per second. So when you learn these strange things about Oumuamua, the local standard of rest angle, its bizarre axis ratio of up to 10 to 1, etc., let's talk about who you reached out to.
I was so surprised by the unusual properties of this object that I wrote to Yuri Milner.
Could you give folks who don't know a brief background on who Yuri is and what his breakthrough initiatives are?
Yes, so Yuri is an entrepreneur from Silicon Valley that has a background in physics, and he's particularly interested in the search for life in the universe and has initiatives that he's funding at the level of $100 million each. One of which is Breakthrough Listen, to try and search for extraterrestrial civilizations, looking for the radio signals, maybe optical signals. And the second initiative that is prominent is called Breakthrough Starshot. that he asked me to lead, which is an attempt to visit the nearest stars and take photos of the habitable planets in it. So, for example, Proxima Centauri has a habitable planet next to it, Proxima b, and the idea is to send a probe that will take a photograph of it. He asked me to lead the Breakthrough Starshot initiative and see if there is a technology that allows us to reach a fraction of the speed of light, such that within our lifetime, both Yuri and I are 56 years old, within our lifetime, we will see the image of that planet. And since the nearest star is 4 light years away, you need to move the spacecraft at least a fifth of the speed of light so that it will get there within 20 years or so. And so I agreed to look into the possible technologies and found just one. And I recommended that we explore or develop the technology of light sails pushed by a powerful laser beam.
Let's talk about how that works, if you don't mind. The basic idea is that you launch something that unfurls something that's like a sail. It's got a big surface area.
Right.
And then you fire photons. You fire light at that thing from the Earth, from a very powerful laser. And those photons, even though they're almost completely immaterial compared to anything that we deal with in our normal lives, each time one of those hits that sail, it does exert a little bit of force. And as with wind pushing a normal sail, you can fire that laser over a period of time and that thing will accelerate and accelerate. How long do you fire the laser at that sail to get it to its top speed after it leaves the Earth?
It will just take a few minutes.
Really?
Yes.
That's it?
And the laser has to have a power of 100 gigawatt or so. And that's roughly the amount of power that was needed to lift off the space shuttle. And the same amount of time, a few minutes. And except that it's delivered to a single gram of matter, such that it reaches a fifth of the speed of light.
So the gram is the payload.
Yes.
All the electronics and sensors and things that science can miniaturize in the intermediate future.
We already have that in cell phones. It's basically a camera, a navigation device, and a communication device, and that can be packed into a single gram. And then another gram would be the sail itself.
What would the diameter of that sail be roughly?
Of the order of 4 meters or so.
4 meters, and that's another gram. And literally in just those few minutes, it's already at a fifth of the speed of light?
Yes.
You're kidding!
At 5 times the distance to the moon. That's the launch distance.
Sorry, this is blowing my mind. Okay, so you launch this thing. Well, it's probably in orbit. You've probably put it up in a satellite. It's in orbit. It's unfurled. It's ready to get zapped, right?
Right. I mean, there is a mothership that releases.
There's a mothership that releases. It's not like we have a 2-gram rocket ship. So it's out there. You point a laser at that thing, and within 5, 6, 7 minutes, it is going at a fifth the speed of light, and it is 5 times past the moon.
Right.
Whoa!
After the first few minutes, there is a journey of 20 years to get to the star.
Yeah.
So it's 20 minutes of excitement, and then 20 years of waiting period. And then once it takes the photos, it takes another 4 years for the signal to reach us.
So it's 24 years after launch.
Yes.
There is actually a history already of functional solar sails because the Japanese Space Agency put together the Icarus project, wasn't it, in 2010?
Right.
And that was the first deployment of a solar sail, and it was fairly successful, correct?
Yeah, it was a demonstration that the sunlight can push on a sail and bring it to a higher speed.
So that wasn't using the laser or any of that, and it was a more traditionally dimensioned spacecraft. What was it, to Mercury or Venus or something like that?
Well, yeah, but the sail was relatively far from the sun, and so the push was not very significant. It was just a demonstration of the principle.
But it got up there, and it was catching solar photons as opposed to laser photons. Reflecting.
Yes.
And they were able to demonstrate, hey, this works.
Exactly.
By the time Oumuamua disappeared from Hubble's view in January, the consensus view in the broader astronomical community was like, it's an asteroid or it's a comet. It's a comet or an asteroid. That was generally where the debate was, correct?
Yes.
And then the cometary explanation got a great deal of momentum in the June timeframe when a paper came out in Nature, one of the very best regarded publications in the world of science, that analyzed a great deal of data that had been gathered during these few months of observation pretty rigorously. There are a lot of names on that paper, a lot of very well-regarded scientists, including Karen Meech. And that paper made the astonishing conclusion that as Oumuamua was leaving the solar system, exiting away from the sun, it started to accelerate, which is not what you normally expect to see happen. Analyzing that acceleration, this team came to the conclusion that Oumuamua was a comet. Would you care to explain how they got to that conclusion?
Yes, so comets have ice on their surface, and this ice when it's warmed up by the sunlight, it evaporates. And you end up with a situation similar to a rocket, where there is gas flowing in one direction and pushing on the exhaust in the other direction. And so the idea is that in principle, comets deviate from an orbit that is shaped purely by the sun's gravity because they have this extra push from the gas.
Which is called off-gassing, correct?
Outgas.
Outgassing, yeah.
Now, the only problem with this idea is that we haven't seen any cometary tail. There was no evidence for either gas molecules in the vicinity of Oumuamua or dust, which is often accompanying the evaporation process.
Did we look closely enough that we really should have seen it? I mean, we had all those telescopes pointing at it.
Yes.
And also there was no coma, right? Which is the fuzzy area that surrounds the front of the comet where stuff is also outgassing, correct?
Right. And also, just the other day, I made a rough estimate. If you ask which fraction of the mass of Oumuamua needs to be evaporated in order for it to get enough push, it's actually substantial. It's more than a tenth of its mass.
Would have had to outgas in order for it to get that thrust. And is that atypical of what usually outgasses from a comet?
Well, not so much that, but you would notice it because there would be a lot of stuff.
Yeah. When the paper came out, I read interviews with a couple of the scientists, and they did acknowledge, hey, it is kind of weird that there was no tail. One of them said, well, that might be because instead of small particles, which for whatever reason are easier to see, the tail may have been comprised of large particles, which are hard to see. And I'm not equipped to parse that argument. How do you respond to that?
Well, there are other effects that outgassing has on an object, because usually the comets are not symmetric, and so they're not pushed just away from the sun, they're also pushed sideways. But moreover, they get spun up or spun down. There is a change in the spin period of these comets. And
there's an eccentricity to the rate at which it's spinning.
Yeah, well, the force is not even on the two ends of the comet.
As a result of the outgassing.
Yes.
Yeah.
And as a result of that, the period of rotation is changing, and the change should have been easily noticed. That didn't show up.
And a couple of other things that I've seen noted was it had different reflectance from typical comets. I think a comet is typically in the range of 4%, and this had a reflectance of 10%.
Or even more.
And tell us what reflectance is and the consequence of that, to your mind.
Yeah, so sunlight is shining on the object, and a fraction of it gets absorbed, and that heats up the surface, and the rest gets reflected. And in principle, the reflectance is what we see as observers. The absorption heats up the object. Now, the Spitzer Space Telescope looked at the heat that this object radiates, and they didn't detect anything. And from that, they inferred that the absorption of sunlight by the object is smaller than one gets typically in comets. And in fact, it reflects much more of the light that falls on it. Now, the fact that they haven't detected any heat or any emission from the object sets an upper limit on its size, and implies that its size could be actually smaller than previously thought. So previously, when people estimate a length of a few hundred meters and a width that is 10 times smaller, they based it on the typical albedo or reflectance of rock, the way we see in asteroids. But if this parameter is different, if you have perfect reflectance, for example, then the object can be 20 meters in size. And so the question is, how big was it?
This became something of a mystery. Now, my understanding is until this paper came out in June, it wasn't widely known at all that this thing had started accelerating.
True.
So that was the first you'd heard about it.
Right.
You'd had some interesting thoughts about it when it first showed up, but this Nature paper comes out in June. It shows demonstrably that the acceleration was there. The authors pointed strongly at the cometary theory. We've obviously talked through some of the visible arguments against it being a comet. In addition to that, what led you to think this might be a completely different force that's causing this acceleration?
It was a paper that appeared on the archive arguing that indeed the spin rate of this object should have changed if there was outgassing.
The spin rate argument, did that appear at the same time?
No, it appeared just a couple of months ago, and it was written by Roman Rafikov from the University of Cambridge in England. And that, to me, was a red alert, because what is then providing the extra push? It's always possible that the observers got it wrong, but they claimed very high statistical significance for the detection, 30 standard deviations. We are usually happy with 3 to 5 standard deviations to give the Nobel Prize to a discovery, right? Here it's 30, so it was beyond any reasonable doubt that there was a deviation from the orbit shaped just by gravity. And so Then the question arises as to what gives it a push. And the first thing I thought about was maybe if the object breaks into pieces so that one piece gives a kick to the other. The problem is that it will be an impulsive kick.
What does that mean, an impulsive kick?
That it happens at one particular point in time.
There's a solitary kick if it breaks apart.
A sudden push. Instead of what was observed, which was a steady push across an extended period of time. So it cannot be a sudden event. Therefore, this explanation does not hold water. And the only other thing I could think of was that it's the sunlight pushing on it. And of course, I was inspired to think in this direction because of the involvement in Breakthrough Starshot. We are always limited in our imagination by what we know. I admit that, and that's true for everyone. But it doesn't mean that what we imagine is not true.
In order to explain the data that the nature team had established.
Exactly.
So your question is, if it's solar radiation, which I imagine is a much smaller force than outgassing, is that correct?
Yes.
So if it's this much smaller force, and if the nature data is right, what would the dimensions of this object have to have been?
Yes, it needs to be a thinner object than a chunk of rock because the force is smaller, so you want the amount of mass associated with the object to be smaller for the same surface area. Now, if it's a good reflector, the size of the object needs to be only 20 meters, not hundreds of meters. The hundreds of meters estimate was obtained assuming that it's a rock.
By assuming it was a rock, they assumed that it had the average reflectance of the typical asteroid in our solar system.
Exactly. So this one potentially could be just 20 meters if it's a perfect reflector. And then the question is, how thin should it be? And we calculated that it should be thinner than a millimeter.
Could we talk about what might produce such a thing naturally?
Right. So I tried to think about that, and I'm a pretty imaginative guy. I wrote over 700 papers in my career, and I just couldn't think of anything natural that would produce it. It doesn't mean that it doesn't exist, but in the interstellar medium or interplanetary environments, you often make round objects, okay? Because round objects tend to be more sturdy, they survive their environment, and also gravity makes things rounder. So it's very difficult to imagine a sheet matter being assembled. I mean, we do manufacture such sheets of matter industrially, but it requires very special conditions that do not arise naturally.
So we have not seen any 20-millimeter thick disks.
Right. The only question is, who produced it?
Right. And you said this could well be an extraterrestrial artificial object, a solar sail, perhaps debris, kind of like you might find an ancient sail floating on the ocean from a long ago shipwreck. This might be debris from an alien spaceship.
Well, yes. A few months earlier, I wrote an article in Scientific American where I talked about space archaeology, which is an interesting concept. In the past, people thought about searching for alien civilizations by listening, trying to find signals. But it occurred to me that maybe the reason we don't find signals easily is because these civilizations are short-lived. Just like our civilization, once we started developing the advanced technologies that we have now, the rate of progress is accelerating. It's exponential. And so that implies that very quickly a civilization reaches the point where it can easily destroy itself, either through nuclear wars or through changing the climate of its planet or polluting its atmosphere. It would mean that when you look at planets that used to have living civilizations, you might find debris or some infrastructure that was developed. Even though there is no life there, you would see evidence for poisoned atmospheres, for megastructures, for photovoltaic cells coating the surface, all kinds of things that you can see from a distance. And finding those relics of dead civilizations would serve a very important purpose. It would teach us a lesson to get our act together and to get along with each other so that we don't share the same fate as those dead civilizations.
So you not only made the solar radiation argument and pointed out these exotic dimensions, but then you took it another step. Quoting directly from your paper, a more exotic scenario is that Oumuamua may be a fully operational probe sent intentionally to Earth. Probably not a sentence that typically appears in peer-reviewed academic journals.
I'll be glad to explain it.
I'd be mortified if you didn't explain it.
If you just assume that the object is one out of a random population of objects, you need 10 to the power 15 such objects to be ejected per star in the Milky Way galaxy.
Is that quadrillions or quintillions? 10 to the 15?
1,000 trillions, if you want.
So quadrillion. Very, very large money.
Number.
Yeah. In order for something to just happen to come close enough to us for us to see it.
On the period of time that Pan-STARRS was operating.
Yeah, during the now 8-year life of Pan-STARRS. So Pan-STARRS has been operating for 8 years. It has a limited range of view, so limited that we didn't even see Oumuamua until it was well on its way out. And this is a calculation you did before Pan-STARRS switched on, right?
Right.
And so if you take that period and you say, what are the odds we're going to see something eject the expected manner, leaping from an Oort cloud? Every star would have to create a quadrillion objects that fly out randomly, every star in our pack.
No, in the Milky Way galaxy.
Oh, in the Milky Way galaxy. There should be a sea of these things zipping around.
Exactly.
Right? Your calculation was that every star in its lifetime, not in 1 year, but over the course of its multi-billion year lifetime, would have to create 1 quadrillion objects.
Right.
And that's a lot.
It's a lot.
And your estimate was what?
100 to 100 million times smaller. There were uncertainties in that estimate. Given all the uncertainties, we expected an abundance which is far smaller. But observing Oumuamua allows us to calibrate how many such objects should be out there. Now, this is unusually high, both for natural origins as well as for artificial origin, because if you imagine launching sails, you need to do it every hour or so to reach huge numbers, and it just doesn't sound reasonable.
So that's an interesting point. So if your calculations were correct and stars simply aren't launching this much stuff, we could get imaginative and say, okay, little green men are launching these things, well, launching these sails, and they're launching them all over the place, but they'd have to be launching a staggering number of them for us to just happen to see one by your calculations.
Right. They would need to do it every few minutes to an hour in order to reach the abundance necessary. So imagine how many such sails should be launched per star. And that's assuming that the civilization lives the full age of the universe. And in fact, if it's short-lived, it doesn't have as much time. And so this doesn't sound quite reasonable. And so how do you avoid that? Again, I'm going in a path very similarly to the maxim of Sherlock Holmes. When you rule out the impossible, whatever remains, however improbable, must be the truth. That's what Sherlock Holmes said. So here I'm following this logical path. And if I want to avoid this huge number, then the only way out would be to say, well, it's a special object that it was sent with a purpose. It's targeting the central part of the solar system, that the habitable region where life could potentially exist. And this is a probe that is on a reconnaissance mission.
And that would explain the sheer happenstance. Now let's talk about your paper and, first of all, its history, its timeline. The Nature paper analyzing the motion, the acceleration, all that came out in June. It was, I think you said, about 2 months ago that the second paper came out that said that we did not see the rotation that we should expect in a comet. That was really what triggered your thinking, I'm guessing?
Yes.
So you and your postdoc finished your paper, and on Friday, the 26th of October, you submitted it to
the Astrophysical Journal Letters, which is the most prestigious journal for rapid communications in astrophysics.
When you say for rapid communications, what does that mean?
Usually the letters section involves shorter papers that are on a timely subject that needs the attention of the community on a short basis, so that don't need to wait a lot of months before the paper comes out.
So Astrophysical Journal letters section, this is the things that are timely. And you also put it up on
the archive.
On the archive. Tell folks what the archive is.
The archive is an online service where we post our papers such that members of the community that work in astrophysics can look at the paper and send us any critical comments they might have. And the paper is basically available online for anyone to read.
From the moment you submit it to a journal, and that's typical process in astrophysics.
Well, I prefer to do that at the time of submission to the journal, because if I get any comments from the community, then I can make changes. If I do it after it was accepted for publication, then you cannot revise it.
Got it.
I care mostly about the substance in the paper, so I want to receive as much critical comments as possible. Some people prefer to get the comments from the referee, because at least it went through one layer of criticism.
To drill down on that for those who are less familiar with the academic process, that means when you submit it to a journal, you typically get comments back from a peer review type of thing. And so some people may not want to put it onto the archive until after they've gotten that first round of feedback.
Exactly.
Maybe they made a silly mistake that the referee pointed out. But your personal practice is to put them up at the moment you submit.
Well, yeah, and the reason is that by now I have a good intuition and a lot of experience. Also, frankly, I realized over the years, many times, my colleagues are less kind to innovative ideas than Mother Nature is. And so it's best to put out an idea without suppressing it. Unlike politics, I should emphasize, in science, we thrive for information. The more information we have about anything, the better is our understanding. The problem is that most of the time you don't have enough information, so there is a period of uncertainty. And some of my colleagues, they prefer shut the doors, not tell the public until we have a clear understanding of the outcome. Because the argument is, well, if they see that there are some unsettled issues that the community is not sure about, then the public will not believe global warming. I say exactly the opposite. I say that if the public realizes that it's a completely transparent process, then the public will give you much more credibility. Part of the problem we have these days is that the public feels that science is the occupation of the elite, that somehow information is being processed in a way that is not transparent. I would like to show the scientific process as it unfolds. There are long periods of uncertainty when you don't have enough data. And I'm not afraid to be wrong. You just need to put on the table all the options, all the possible interpretations of the limited evidence you have, collect more data on Oumuamua or other objects in its class in the future, and eventually figure out the truth.
So your paper was submitted. It was accepted rapidly. You said 3 days, right?
Yes.
Now, this is the rapid response team of Astrophysical Journal. Is 3 days typical for them?
No, it's very unusual. Normal is a few weeks or month for the response. We're talking about a factor of 10 faster response than usual, but moreover, it was actually published 2 weeks after submission.
2 days ago, right?
Yes, so it's about 16 days after submission. That's extremely unusual. I had another paper that was similarly fast.
You published over 600 papers, right?
700.
700.
Yeah.
So this is in the top 350th in terms of speed for your own personal.
Right. To tell you the truth, I didn't plan on having any press release.
Are there typically press releases for papers? Like what percentage of papers might have a press release?
1 out of several tens or 1 out of 100. I have to decide ahead of time. And first of all, we don't have a public affairs officer right now here at the Center for Astrophysics. So there was nobody to actually process a press release. But moreover, we don't have clear evidence that it's artificial. And so I didn't want to make a big fuss about it. Then there were a couple of bloggers.
And I have to give them shout outs. Centauri Dreams was the first one to pick up on it. A blog I had not heard of before. They picked up on October 29th, so 3 days after you put it up on the archive. And I will say, I read a ton of responses to your paper preparing for this conversation. To this day, I would have to say Centauri Dreams did the most rigorous, imaginative, careful deep dive of anything I've read. So Centauri Dreams, and then another great blog, Universe Today, a couple days later come out. So 4 or 5 days go by. These two blogs are writing about it.
The same bloggers wrote about my previous papers. One is Paul Gilster and another is Matt Williams. And so I thought that would be it.
But then it broke into the mainstream press, I want to say around the 5th or 6th. So the bloggers pick up on it. There's a few days of relative silence. And then do you have any idea how or why it broke into the mainstream press?
I believe it must be social media. I have no direct evidence because I don't have any social media presence.
Yeah.
And so I have no clue as to why it went viral, but I was supposed to go to Germany, Berlin, to give a keynote lecture on starshot and space exploration. And so I was about to leave to that trip. And at 6 a.m., I started getting requests for interviews. And by 10 a.m., I had 4 television crews come to my office here at Harvard. And then another one came to my home just before I boarded the taxi to the airport. And I used this as a platform to explain the scientific methodology of an anomaly appearing in the data. The standard explanation, in this case, it's cometary outgassing, not being able to explain it, and then seeking an alternative interpretation, publishing a paper about it, and then looking forward to having more data to decide whether it's right or wrong. And this period of uncertainty is an integral part of science, and I wanted to explain that. I regard being a scientist as a great privilege of maintaining your childhood curiosity, because children ask questions, they are not afraid of being wrong. Somehow, when they become adults, the adults lose that innocence. And that includes scientists as well. Many of my colleagues are not willing to take risks, not daring to be wrong. And that's a problem because sometimes we just don't know in advance what's right and what's wrong. And we have to take the risk in order to make discoveries, because what I want to understand is what Oumuamua is. And for that purpose, it doesn't really matter how popular is one idea versus the other on Twitter. It is what it is, and we want to find out.
Now, you're alluding to Twitter. As I started researching this story, one of the things that first took me aback was like, wow, there is a lot of negative reaction to this. And the first really harsh rebuttal I personally saw was in the Washington Post. And it was very widely quoted beyond that in a lot of online publications that I respect. And what it said was the following: no, Oumuamua is not an alien spaceship, and the authors of the paper insult on a scientific inquiry to even suggest it. And I was like, wow, we have a brawl here. And at that point, I'd spent well over an hour reading your paper and its dozens of citations and the frankly terrifying math that it has, which went over my head. I wanted to dig into this contrary case. This is the Washington Post, right? And it turned out the Washington Post's authoritative, carefully researched source turned out to be a tweet which featured no link to an article or any other support of this very definitive, vicious, and rather ad hominem attack. And so I started digging deeper, and it turned out that the tweeter, someone who works at a family-oriented science museum in Columbus, Ohio, he claims some sort of Ohio State affiliation. Now, I'm going to be very clear. I am not a credentialist. The fact that you're chair of the astronomy department at Harvard is meaningful to me, and I certainly respect it. But I would never take an audacious claim from you as received wisdom merely because you said it. And likewise, I would never reject any rigorous original argument merely because it came from somebody at a science museum. I mean, Einstein was a patent clerk. Genius is everywhere, right? So I'm not trying to be elitist about the credentials, but it was astonishing to me that the Post presented this as a counterbalance to your rigorously researched paper. I dug deeper because I figured this guy must have done some kind of very measured rebuttal that I'm just not finding. And all I could personally find was a weird rambling video in which he made statements about what you must have been thinking when you wrote this. So I cite that as a little bit of dismay about how the press works in this day, where somebody might do a long investigative piece and then somebody else might say, nah, fake news. And those are considered to be equal things. But also I point to that as just a sign of the fact that there is some genuine anger that your paper released. Visceral anger. And by the way, this gentleman is a PhD. He's not an outsider to the field. He is pissed. Where does that anger come from? Is it using the A word? Is there a thing in astrophysics, the alien? You're not supposed to say that.
I would say it's prejudice. Many people think they know the answer in advance. In that sense, we haven't progressed much since the days of Galileo. Even though we have science as one of the most important achievements of humanity, people still have a lot of prejudice about what the outcome of science should be. And they want to see that answer. Quantum mechanics was discovered as a result of experiments. And Einstein had this emotional reaction to it. He didn't like that theory. He thought that something is wrong with it, and he wrote papers about it, but Einstein was wrong. So Einstein made mistakes, and the reason I point this out is that anyone can make mistakes. Therefore, one should remain humble. The academic community has this concept of tenure, where someone has faculty position for life, irrespective of what happens, okay? As long as that person doesn't commit a crime. That is a great privilege. It's a privilege to follow ideas to where they lead you without worrying about what other people think. However, many practitioners in academia do not use that privilege. Once they get to the position of tenure, they worry about their image and about not being wrong. And by doing so, they betray the purpose of their profession. The tenure process is aimed at allowing you the freedom of coming up with your own conclusions. And therefore, if people have a problem with this idea, they should come up with a specific alternative interpretation of the extra push that Oumuamua has, rather than calling names or saying things without scientific context. At the same time, the public would appreciate a honest debate. Many of my colleagues would say, if the public is interested, it's not sophisticated enough, and therefore it should not be explored. I say, who cares about what people say? Nature is what nature is. And I try to understand it. And if it happens to be alien civilizations, and people are very excited about it, that's great. If it happens to be the nature of dark matter, and people don't care about it, that's fine with me. I don't care about Twitter, Facebook, what people say. I want to understand nature, and I think nature is always beautiful. The only thing that can be ugly is human-made. One of the reasons to explore space is because you can see nature left on its own. But if you go to the beach, and I like to do that on vacation with my daughters, and you look at seashells that were swept ashore, you see all kinds of seashells that came from different origins. And every now and then you see a plastic bottle, which came from an artificial origin. And I think the same approach should be adapted in the context of looking at all the interstellar objects that arrive at our door and examining each and every one of them, even if Oumuamua is natural in origin. First, we learn about a completely different process that makes this weird class of objects with much larger abundance than we ever expected. But in the more interesting case, we might learn about another civilization. And without a prejudice, we are just collecting data about the universe.
Now, some of the folks who have come out negative on your interpretation are very well-regarded people. And I'll quote one person that I happen to know. I don't know him terribly well, but Seth Shostak, who is with the SETI project. I did a little bit of work, actually, with SETI when they were doing something with the TED conference. Got to know Jill Tarter, which was really fun and a huge honor. And I met Seth a couple times since then. And I think you both wrote in notes to something, I'm trying to remember, it was like Galaxy Today or another really cool blog that I discovered through reading all this. And Seth said, and I'm quoting from his email that was reported in this blog, "It's true that the Harvard paper suggesting that this object might be engineered rather than simply the 10 millionth rock from the sun." And I'm going to skip a little bit. He then later says, "The idea of alien companies perennially been interesting to the public. Personally, I think that's because we're hardwired to be curious about potential competitors, or if you're in the abduction mindset, mates." And then I'll skip down a little bit further. "We wish to believe that Homo sapiens is interesting and significant enough to warrant visitors from some other world. Obviously, that's kind of self-centered." Now, again, I'll say Seth is very well regarded. He works for the Search for Extraterrestrial Intelligence, so he is not somebody who is going to deny the likelihood or the existence of aliens outright. How do you respond to that kind of a signal from him as opposed to completely unresearched and unattributed?
Well, this is very interesting because I interacted with the SETI community for a while now, and it looks to me that they have a reverse psychology where they try to deny any evidence because they are worried about the cry wolf. And I'm guided here by my science. I basically follow the method that I will use to interpret data on the first stars in the universe or data on the microwave background or anything else. I try to come up with a theoretical interpretation that appears to me as the most likely. And in this case, it's the most likely because I couldn't think of anything else. And the point that is most important to me is that this is not a speculation. We know that we exist, that there is both primitive microbial life as well as advanced life here on Earth. We know that about a quarter of all the stars in the Milky Way galaxy have a planet of the size of the Earth in the habitable zone of their host star so that they can have liquid water on the surface and the chemistry of life as we know it. And so if you roll the dice so many times, what's the chance that we are unique? I don't think we're special. I think out of modesty, we should admit that this is not a speculation, that in fact, we just need to go out and find evidence for life, including intelligent life. Now, if you look at speculations in science, there are plenty of speculations these days. For example, the mainstream of theoretical physics advocates extra dimensions beyond the 3 spatial dimensions and the 1 time dimension that we live in. That to me sounds like a wild speculation because we have no evidence for it. Searching for another civilization that is similar or more advanced than ours under conditions that we find to be exhibited in many other planets is not a speculation. It's just looking for another system that resembles a system that we know exists. And so I don't regard the search for life as a speculation because we know that it's quite likely that we are not special. Whenever we thought that we are special, we were proven wrong. When we thought that we are at the center of the universe, it turned out to be wrong. We are not at the center of the physical universe. And why would we believe that we are at the center of the living universe, the biological universe?
Right. Let's assume momentarily this does turn out to be one of those false alarms. What are a few of the things that could turn out to make this mundane? You did base your calculations on this work in Nature.
Right.
They came out with 30 sigmas. I mean, they were very, very certain of their data, but it's not out of the question that there was something wrong in their math.
Definitely. And so that's the first thing that one should worry about. And I encourage other groups to analyze the same data and figure out if they agree.
Another thing, I want to say June, around the time that the Nature paper came out, I started reading about all the things that were anomalous about the comet. The lack of the tail, well, it could be explained by larger dust. The lack of gas, particularly a gas called CN gas. which is often looked for because it's particularly bright and easy to spot, but it also is highly indicative of the presence of water. And so it seems that this thing was a waterless comet, which is a very unusual thing. The reflectivity of being 10%, well, it has very unusual thermodynamics for a comet. So that at first really threw me. But then I saw a couple of quotes that like, okay, this is coming from somebody else's Oort cloud. We know little enough about what's in our Oort cloud. We know nothing about the chemical and other attributes of things in a distant Oort cloud. So my question to you is, do we presume that there's a fairly homologous presence of chemicals and planetary system and solar system development processes that would make us presume that other Oort clouds have similar objects? Or is the fact that this is a Panamanian at our dinner party might just account for a whole bunch of things that would otherwise seem weird if we knew it was a next door neighbor?
There could be conditions under which you produce unusual objects, but the first visitor should not be an outlier. Statistically speaking, you expect it to be typical. Moreover, the fact that this is the local standard of rest, this object, means that you can't just eject it from the edge of the Oort cloud without giving it a significant kick in exactly the opposite direction from the motion of its parent star, such that it will be at the local standard of rest. And so there are many peculiar things. So the point is that this is not what you expected for your dinner party. Why don't we discuss it? Why don't we put all the options on the table? Since we don't know if we are alone, why don't we put that option as well? What is there to lose? To me, it sounds like a logical possibility, given that we exist and that we had Voyager 1 and Voyager 2 that left the solar system. Why wouldn't we consider the possibility that it's artificial? What is there to lose by having that option on the table?
This reminds me, there's one element of the local standard of rest argument that we didn't get to that I don't quite understand. So if it is at the local standard of rest, we've already established that the odds of that happening naturally are roughly 1 in 500. Why might somebody doing things artificially want to target the local standard of rest? Would that make it for a more efficient journey or make it easier to sneak up on us?
Well, if you establish a relay system, for example, of posts where you have an array of such stations, then you place them at the rest frame. Like if you put the buoys on the surface of an ocean, you put them there at rest because stars will whiz by, but they remain there.
So that might be a navigation system.
There could be a purpose behind it, but first we need to figure out if it's natural or not. Whenever there is a reason behind something, if it has a purpose, then the likelihood of having it naturally is very small. And so a signature of something artificial is that it's not easily produced naturally. And we see that, for example, when we have industrial pollution, the molecules that pollute our atmosphere cannot be easily produced naturally. And that's why, in principle, if we detect these molecules in the atmosphere of another planet, that would indicate an advanced civilization over there.
So what should we do now? We've seen this anomalous object. At a minimum, it's the first thing to come from outside of the solar system. That's exciting. It may well be artificial in your view. It almost certainly isn't in the view of others in your field. Everybody's intrigued, though. So what should be the research agenda over the coming decades to nail down more understanding of extrasolar system objects?
Yeah, so the importance of my paper, the way I see it, is that it alerts people to the importance of getting more data and more information on objects of this class. And that means that when the next one is spotted, the best telescopes on Earth will collect the data on it. And so I think the way to proceed is to find more of them. Indeed, the astronomical community is constructing right now, as we speak, the Large Synoptic Survey Telescope that within 3 years will start giving us data. And digging through that data would be very exciting. So I very much look forward to that.
Is it earthbound or is it?
It's earthbound. Yeah. And it's the highest priority in a process that the astronomy community goes through every 10 years, where the astronomy community defines its goals. And the Large Synoptic Survey Telescope was recommended as top priority in the previous decadal survey. And it's now being completed. Within 3 years, we start having data. And now we have another target for it, which is to search for those interstellar objects. And that would be very exciting.
So this will be far better than pan-stars at finding things?
Yes, much fainter things can be found by it than pan-stars can. And moreover, it will monitor the sky more frequently with better cadence and better sensitivity. So overall, it's a much better survey telescope than pan-stars is.
So take just sort of an arbitrary number. If pan-stars is configured to spot 1 Oumuamua out of 1,000, the Large Synoptic Survey Telescope, is it configured to maybe spot 10 out of 1,000?
It's a little more complicated because since it's much more sensitive, it could see objects that are smaller.
Smaller still, yeah.
Yes, and we need to know the size distribution, how many more smaller objects you have relative to big objects. It's many orders of magnitude better prospects for detection with LSST than with pan-stars, and the exact number depends on the size distribution of objects.
So was the Large Synoptic Survey Telescope specifically designed to find objects from outside of the solar system? Is that its principal mission?
No, its principal mission is to monitor exploding stars,
supernovas and
supernovae, or other transient events at great distances.
Gamma ray bursts, things that happen suddenly, briefly, and rarely. It's meant to capture a higher percentage of those.
Yeah, flares of different sorts that result from explosions of stars or other sources. So that's the transient universe. You don't just take a single snapshot of the universe, but you take many snapshots, multiple nights of the sky, and it opens the door for finding out how the sky changes. In the meantime, you can also see moving objects if they are close to you. That's how pan-stars found Oumuamua.
So with the LSST coming online, even though it wasn't specifically designed to look exclusively for items outside of the solar system, it sounds like it's going to be a lot more sensitive than pan-stars. So if pan-stars in its 10-year history was able to find one Oumuamua-like object, how many Oumuamua-like objects would you expect the LSST to find over, let's say, a 10-year span?
Well, orders of magnitude more.
Tens, hundreds, thousands.
Even more than that, it depends on the size distribution of those objects, because there are many more smaller objects than big objects. Then you would find them nearby because they would pass near us. They're much more numerous, so they have a better chance of passing near the Earth.
And pan-stars would have missed those smaller things because it can only see Oumuamua and bigger, let's say.
Exactly. Yeah. So the sensitivity of the telescope allows LSST to see smaller things. As a result, it would see more things. And the question is to how many more objects that are interstellar it would find depends on the distribution of sizes. Those objects, so we don't know it for sure, but it will definitely be orders of magnitude, thousands or more, millions, depending on the size distribution. And that would open a completely new window into the origin of these objects, because we will have a whole collection, and perhaps even a small minority of those that look peculiar would be of great interest. Having a large number of them would help us, statistically speaking, figure out where they came from, what could be the circumstances that allowed them to exist in the first place.
And so with many orders of magnitude more objects likely to be spotted, within really just a few weeks or even a few days of that telescope coming fully online, we should expect to start seeing things.
That's right.
And if a long span of time goes by and we see nothing, let's say 10 years go by, and we see no more Oumuamua-like objects of any size, what does that tell us?
Well, it tells us that the guest we had for dinner was very special and had a purpose for visiting us.
Well, Avi, I know with the news that has broken and all the attention that your paper has gotten, again, as I said at the beginning, this simply has to be one of the craziest weeks of your professional life. So I really want to thank you for taking out so much time to explain your perspective on all this and where you think this is going.
My pleasure.
So what does it mean if we turn on the big telescope in 3 years and we see nothing quite like the strange object we found in the small telescope? Say it again, Avi.
Well, it tells us that the guest we had for dinner was very special and had a purpose for visiting us.
That certainly ranks as one of the cooler sentences I've been on hand to hear. I mean, it would be a great line in a movie. But this is real life. And that was the chairman of the astronomy department at Harvard talking about an interstellar object that passed fairly close to Earth about a year ago. If that just doesn't give you a little bit of a shiver, then you're not a science fiction writer. I know most of you aren't, and be grateful for that. It's an affliction, believe me. Anyway, as we discussed during our interview, Avi has gotten a certain amount of heat from the astrophysical community for his heterodox interpretation of Oumuamua's origin. And in retrospect, I can't help but wonder if aliens aren't just something of a third-rail topic in his professional community. For instance, I'm sure astronomers get tired of people buttonholing them at parties wanting to talk about UFOs and their alien pilots. Surveys indicate that somewhere between a quarter to a half of American adults believe that aliens have visited the Earth, whereas I personally haven't ever met a professional astronomer who shares that belief. On the flip side, another very large group of people is fond of ridiculing the very concept of aliens, possibly because the first group contains so many irritating weirdos. But astrophysicists are deeply aware of the immensity of space, the yawning abundance of habitable planets, and the vast timescales that the universe has had to experiment with life. This makes them very open to the possibility that intelligent life is widespread out there, even if they do not believe that UFOs constitute proof of this. So this is a formula for a very different set of frustrating conversations with clueless members of the general public who have very strident opinions about something connected to the astronomical profession. If I were an astrophysicist, I'd be tempted to suggest that we all take a secret professional vow to stay mum on this toxic topic unless somebody comes up with some form of overwhelming proof, which of course is exactly the sort of conspiracy that the X-Files crowd would expect. So maybe all of that is the source of at least some of the frustration that Avi has encountered from his colleagues, or maybe I'm just trying a bit too hard to be a shrink here. Whatever you think about this controversy, we should all be relieved that Avi has put something of a sell-by date on it, as I mentioned in my introduction. By his own calculations he's been working on off and on for over a decade, an argument-settling number of observations should be made very soon after the Large Synoptic Survey Telescope points its gaze deep into the sky over Chile in 2022. If Oumuamua is a natural object of a sort that's created by the universe at a steady, regular cadence, we will see many of its cousins shortly after we turn that sucker on. If we do see lots of Oumuamuas, we'll be able to track them closely. We'll be able to see how normal it is for them to accelerate as they leave our solar system. We'll see if they typically have tails or not, or if they have tails which for some reason are invisible to normal telescopes. We'll learn if interstellar objects tend to have water on them, like our local comets, if they tend to have the reflective properties of objects in our own solar system, etc. After learning all these things, we should be able to establish whether Oumuamua was a mundane object or that very special dinner guest that had a purpose for visiting us. And most exciting, this fascinating resolution should come around a bit more than 3 years from now, roughly January of 2022, probably a few months after that. Game of Thrones fans are used to waiting much longer than that for new books, so this is not a delay of cosmic proportions. Now, you have just finished listening to the short version of my interview with Avi. I often post abridged versions of my episodes to the main feed of my podcast out of respect for the time of my more casual listeners, who sometimes get antsy if we get too far past the 1 hour mark. Committed listeners to the show, on the other hand, tend to view more depth and detail as being a feature rather than a bug. And those who make the show possible with contributions of $5 per month or more can access longer versions of 6 or 7 of my shows, including this one, along with many, many other hours of bonus content, which is only available to supporters. These recordings drop right into your smartphone like any other podcast, which you subscribe to via a private link that Patreon sends you when you sign up. So it's really seamless, it's really portable, and it's really cool. If you sign up, you'll get access to the entire archive of bonus material going clear back to February. And I add to that archive every time I post a new episode. Sometimes it's an entirely freestanding mini episode, and increasingly often it's an extended version of the interview from the main podcast feed, like today. I'm leaning into this extended version model more and more, because as the show's reputation is becoming more established, and as I'm gaining confidence as an interviewer, I'm starting to get a lot of time from my guests. Now, I don't want to overwhelm casual listeners of the show with super long episodes, but no way am I going to throw away any of the exquisite insights that my guests share with us, because their time is priceless. And by the way, so is yours. So the extended versions are absolutely worth the additional time for those who wish to access them. All of this is doubly important because for now, this show is free of advertising, as you hopefully noticed. So the only way I can support it is through backing at patreon.com, which, for those of you who don't know the site, as you've probably inferred by now, it's a site that enables precisely this sort of voluntary support. It's a bit like Kickstarter, only for episodic content like podcasts. It is spelled patreon.com, and you can find my page at patreon.com/Rob Reid, and Reid is R-E-I-D. Thanks to my backers, this show's doing a bit better than break even. But due to the time requirements of each episode, I'm roughly clearing my hometown's minimum wage for the time I put into it. Now, New York City minimum wage is quite high compared to most communities, but it's not very high compared to New York City rent. So long term, this won't be sustainable unless I continue to gather more backers and or allow ads on the show. As I've explained in earlier episodes, the show's audience is big enough to attract some advertising, but I'm determined not to allow any advertising until I can really do it in a quality way. So, as many of you have heard many times, I need to grow my audience. So if you're not financially able or just not inclined to back the show financially, you can still help it a lot by spreading the word about it. For each episode, I post a very self-contained tweet, which carefully describes the current show, and the tweet for Avi's episode is already up in my feed at twitter.com/RobReed. So please consider helping the show light up new neurons out there by forwarding these little synopses around. Most of my episodes are only retweeted a few dozen times, actually, so I absolutely notice and deeply appreciate all relevant activity on Twitter. The last and most simple, easy, time-efficient, and free thing you can do to help the show expand its audience is to rate it on iTunes or on Apple's Podcasts app. Both of those apps, frankly, have rather squirrely UIs, but if you made it through today's episode, or frankly, any of my episodes, you're definitely smart enough to figure it out, I promise. These ratings matter to Apple's promotional algorithm and therefore really do help the show expand. For those of you who are in the US, happy, slightly belated Thanksgiving. And for all of you wherever you may be, especially my new listeners on Oumuamua, I hope you join me for my next episode in early December.